Welcome. So far we have learnt how to deduce the model equations from a full-fledged Navier-Stokes equation, and with some assumptions we have made, and also we have seen some of the non-dimensional numbers and their significance. In this particular lecture, we shall continue with the microscopic balance. Now, in this we shall be taking one illustration to demonstrate the similarity between the momentum transfer, the energy transfer and the mass transfer, so that you can understand that if you know how to solve for the momentum balance equation, you can extend your solution for the energy balance as well as for the mass balance or vice versa. So, let us first start with the momentum balance problem. Here we are given a flow near a surface that is suddenly set to linear motion. So, what we have been stated that consider a semi-infinite fluid with constant density and viscosity bounded by a horizontal surface in xz plane. It means semi-infinite means that on the fluid is confined by one surface on one side and other end of the fluid extends to infinity. Okay? And this may be the case when you talk of a say on this particular table. You can see that the air is there on the table and it is moving up. Okay? Or on the earth surface you can say that the air is there on the earth, and on the as we go above it is just extending to a long distance. Similarly, when we talk of a suppose a vehicle is there, okay, whether it's a car, whether it's a train, you see that the air which is in touch with the train or the car, it is also bound on the one side, it is bound by the particular object, and on the other end it is going to infinity, that means to a long distance. So, all these are the examples of such kind of system of a semi-infinite fluid. Initially, the fluid and the surface are at rest. That means, suppose you can imagine that as if a car is standing there, okay, and in touch with the car is the air. So, both the fluid and the car are at rest. Okay. At a time t equal to 0, the surface is set to motion in the positive x direction. That means, you can imagine as if you have started the car and the car has started moving. It can extend for some, it's the same thing about a train also, okay, as if the train has started moving. The velocity Vx is a function of y and t. That means, you now see that the velocity of the fluid will now become a function of the y, that means the distance from the surface and time. Assume the flow to be laminar, no pressure gradient or gravity force in the x direction, and the fluid to be Newtonian. So, these are some assumptions, but these are not restrictive. These are just for demonstration purpose. We have made the assumption, but you can extend the analysis for any kind of fluid, for any kind of flow, and for any other kind of forces that might be acting on the particular system. So, here pictorially we have shown you these situations. Here you can see that at t less than 0, fluid is at rest. So, here we have the surface, okay, and the y direction is away from the perpendicular to this binding surface, and this is the fluid. And at time t equal to 0, this surface is set to motion. Okay. And what happens at time t more than 0, we find that there is some kind of a velocity gradient, that is Vx. The Vx means the fluid is also going to move in the same x direction, but the magnitude of the velocity will keep on changing as we move away from the surface, and you can see the magnitude is 0 at the surface and it keeps increasing as we move away, and ultimately again it becomes a constant value. That means it attains the free stream velocity of the fluid, okay, away from the surface. And this change of the velocity occurs due to the finite viscosity, the viscous effect. If the ideal flow is there, then the viscous effect will not be experienced. So, it will be all the same velocity will be there, okay? There is no viscous effect. Now, as stated in the problem, we are saying that the Vx is a function of y and t, and we are assuming the other two components of the velocity, that is Vy and Vz, to be 0. So, because Vy, Vz are 0, so we have three momentum balance equations. Out of these three, we need to consider only one momentum balance equation, that is in the x direction. Okay. So, this is the x direction momentum balance equation. Here you can see that we have the unsteady state term. This gives rise to the dependency of the Vx on time. These are the inertial terms. This is the pressure force, and this is the viscous force, okay, and this is the body force, and as given in the problem, this body force is taken to be 0. So, because this Vy, Vz are 0, so these two terms are dropping off, okay, and because in the x direction there is no change in the velocity, so this term also goes out. So, what we are left with is rho into dou Vx by dou t, okay, and as stated in the problem, there is no pressure gradient in the x direction. So, this term is also 0. Now, please understand this. In this case, the flow is happening due to the motion of the surface. Flow can happen by many ways, that a pressure gradient also causes a flow, but in this case the pressure gradient is 0, but the motion of the surface is causing the flow. Okay. And in this case we are finding that this dou by dou x terms are 0, dou by dou z terms are 0. So, only we are left with is the dou to Vx by dou y square. So, we are writing this, and the body force term is also taken to be 0 as per the question. So, with this we are landing up with this equation, and then we take the fluid properties, that is density and the viscosity, to be constant. So, because they are constant, they have been taken out of the differential. So, now we take the density on the right hand side, and we have this particular equation. That means dou Vx by dou t equal to nu dou to Vx by dou y square. So, this is the particular equation. If solved, we will get the actual velocity profile, provided we put the initial condition and the boundary conditions. And you can see from this equation, this is a degree 1 with respect to time. So, we need only one initial condition, and this is of degree 2 with respect to y. So, we need two boundary conditions, and let us see how we prescribe these initial and boundary conditions. So, here we have the initial condition. We said that at t less than equal to 0, Vx is equal to 0 as stated in the problem for all y. Okay. And the boundary conditions is that on the surface y is equal to 0, that means it is on the surface, we have the Vx equal to V naught, and V naught is the velocity with which the surface has been moving. Okay. So, this is the V naught. So, V equal to V naught, that means we are assuming that there is a no slip boundary condition. We call it no slip, that is no relative velocity between the surface and the fluid. So, this is the no slip boundary condition, no relative motion between the fluid and the surface at the surface. And then at y equal to infinity, infinity here means that long distance from the surface, where we do not feel the effect of the drag by the particular surface. So, y equal to infinity, the Vx is taken to be 0. In this case 0, because we are saying that the fluid was at rest initially, but it need not be 0. It could have some other non-zero value, suppose V infinity, which call the free stream velocity. Okay. So, in this case, as per the question, we are taking this Vx to be 0 at y equal to infinity for all time t more than 0. Now, what we do? We go for the non-dimensionalization of the particular equation. So, we define the non-dimensional Vx as Vx over bar and define it as the Vx divided by V naught. So, V naught is taken to be the characteristic velocity, that is equal to the velocity with which the surface is moving. So, with this definition, we get this particular equation for the momentum balance in terms of the non-dimensional velocity. Now we see that the initial condition is now that Vx over bar equal to 0, and now for time t less than and equal to 0, and for the boundary conditions you see that for y equal to 0, Vx over bar equal to 1, and y equal to infinity, Vx over bar is equal to 0. Okay. So, we find that this is also a normalized velocity. Next, what we do that we see that both the boundary conditions have been taken as the boundary condition of type 1 or the Dirichlet boundary condition. So, we find that Vx is a function of y, t and nu, okay, only these three. Okay. So, if it is not of type 1, that means it could be a Neumann boundary condition, then you will find that it will also be a function of the flux term, some kind of momentum flux term. So, because of this particular situation, we find that this Vx is dimensionless, and then y, t and nu should appear in a dimensionless form. And you can see that if we define a new coordinate y over bar, and this y over bar we can put in this way, that y divided by under root 4 nu t. Now, this particular way of defining a non-dimensional numbers in terms of the variables which are appearing within the equation is called method of combination of variables, and in this case all the variables happen to be independent. So, we are getting a non-dimensional distance in with respect to the variables which are there already in the particular equation. Okay. And this factor 4 has been taken as some kind of a factor which we will see that how the inclusion of the 4 helps in our the equation. Okay. So, this 4 is not sacrosanct, you may take it or you may not take it, it is not mandatory to have this 4, but looking at the particular equation we obtain ultimately, we find that if we put the 4, then we will be having the equation, non-dimensional equation, which will be quite compact. Okay. So, that way we take the 4 inside. So, now you see that dou v x over bar by dou t may be written, this is purely calculus. So, we find that this will be dvx by dy. Now, why? You see that dvx, we are putting d, not dou, because now you see that with this definition of y over bar, v becomes, this v bar becomes a function of only y over bar. Okay. So, that is why the partial differential is gone, we are replacing the partial with the total differential. So, it is dvx over bar by dy over bar, and but dou y over bar by dou t, because y over bar is a function of both y and t. Okay. So, with this understanding we find that this is coming as minus half y over bar by t dvx over bar by d y over bar, and then similarly dou vx over bar by dou y is equal to dvx over bar by dy over bar into dou y over bar by dou y, and this is this. Okay. And dou 2 vx over bar by dou y square equal to coming like this. Now, what have we done by doing this? We find that we have converted a partial differential equation into an ordinary differential equation. And how does it help? It helps in simplifying the solution of this particular equation. So, now after getting these terms, we put it in our original equation and we find that this is the equation we are getting, and this is an ordinary differential equation. Okay. Now, you see the boundary conditions are now getting modified. Now, we need not talk of initial condition, that has been absorbed already in T. So, this is now coming boundary condition. Now, what we find that y over bar equal to 0, okay, we get that Vx over bar as 1, and y over bar equal to infinity, we get Vx over bar equal to 0. So, this is how we are able to model the fluid motion which is there, a semi-infinite fluid which is bounded by a surface, and the surface is given a linear motion. If we extend this particular problem now, we can extend it for a sinusoidal motion. That means it need not be a linear motion, it have a sinusoidal, and this sinusoidal motion is oscillating like this. So, this oscillation will be in the x direction only, and we say that the displacement from the mean value is taken to be capital X, and this capital X is a function of time and is given by the mean value x naught, that is the amplitude, and the omega is the frequency. Okay. Now, we find that initial condition is the same as before, that Vx equal to 0 for all y. Okay. And the boundary condition is now like this, that at y equal to 0 we are giving dx by dt, because x is the position. So, dx by dt is the velocity. So, we are going dx by dt equal to x naught omega cos omega t. From this particular expression we are differentiating with respect to time, and y infinity equal to Vx equal to 0 as we have done it earlier for all t more than 0. Now, let us put this amplitude of the velocity like V naught equal to x naught into omega, because this is going to be constant. So, we replace this x naught omega by this V naught omega. This is the amplitude of the velocity, whereas x naught is the amplitude of the particular displacement of the wave from the mean value, that is the amplitude. Okay. So, this is now the V velocity of the fluid of the surface is also coming like an sinusoidal motion, and this is in terms of the amplitude V naught into cos omega t. Now, you know that cos omega t may also be written in terms of the exponential form, and exponential form you know that e to the power I t is equal to cos I t cos t plus I into sin t. This we know. Okay. So, this particular cos is the real part and sin is the imaginary part. So, we are writing this cos omega t as this r is signifying the real part of exponential of I omega t. Okay. So, we are writing it is still we are writing in a concise manner. Now, generally in this case situation we are interested to know the steady state solution rather than the transient solution. Okay. And this we find that even if you do not solve it, but we find that the steady state solution will be a sinusoidal with frequency omega, and the amplitude and the phase will be functions of the x. That means that is how it will change. Okay. It will have the velocity of the fluid due to this change in the sinusoidal motion of the surface will also have a sinusoidal nature. That means the Vx will also be sinusoidal in nature, but it will have a phase and frequency that will be changing with the position of the from the surface. Okay. So, I will not be going into the solution of it, we are just learning how to deduce the model equations. Now, we come to a similar situation, but in a energy transfer problem. In this, what we find that we have again a semi-infinite solid material. Okay, you can see the solid material occupying the space from y equal to 0 to y equal to infinity. Okay, so instead of the fluid, now we have a solid material, and that the initial temperature is taken to be T naught. Okay, at time t equal to 0. The surface at y naught 0, that means this if this is taken to be the y not equal to 0 and this taken to y infinity. Okay. So, we find that at y equal to 0, we at time t more than equal to 0, this surface is given a temperature of T1. Okay. And that and it is saying that it is raised to a temperature T1. It is not mandatory we have to raise it, it may be also lowered. Okay. So, it can go either way. Okay. So, if it is in this problem it is raised to T1 and maintained at that temperature for time more than 0. We have to assume that the material to be homogeneous and isotropic, so that we can assume a single value of the solid property in the particular phase and no heat generation within the solid. So, with these assumptions, now again we consider the particular energy balance equation, and we know that temperature is a scalar. So, we have only one energy balance equation, and in this energy balance equation these are the unsteady state term, these are the convective term or the inertial term, and this is the conductive term, and we are neglecting any source term. If there is any kind of generation, so we are neglecting the source terms. Okay. So, with this assumption, and in the solid we know there will not be any convective heat transfer, so that all the velocity terms will be taken to be 0 in a solid. Okay. So, we are having only the unsteady state part, and we are also assuming that the properties of the solid, that is K, the thermal conductivity, the density and the specific heat are remaining constant, so that they have been taken out of the differential, and we are getting this particular equation. And now we are assuming that the thermal gradient or the temperature gradient occurs only in the y direction, so that we are taking the dou by dou x and dou by dou z to be 0. So, with these assumptions we find that we are having this dou t by dou t in terms of the dou 2 t by dou y square. Now, if you look at this particular equation, now you see that this is the thermal diffusivity, okay, alpha. Okay. So, you see that the mathematical form of this equation is exactly the same as we have derived earlier for the semi-infinite fluid with a surface which is being set to motion at time t equal to 0. So, because the mathematical forms are the same, so the solutions will also be the same. Now, in this case we non-dimensionalize the temperature like this, that T equal to the theta equal to T minus T naught divided by T1 minus T naught. And as we know that in this case the temperature will be varying between T naught and T1. So, in this case we find that theta is also normalized. So, it will be varying between 0 and 1. So, with this definition we again put it in our parent equation, and we have this particular equation, and here we are writing the initial condition, boundary condition like this, that initially theta equal to 0 because t equal to t naught. So, theta is equal to 0 initial condition, and boundary condition is that initially the temperature is at t equal to at the boundary that y equal to 0, the temperature is taken to T1. So, we put t equal to T1 here. So, theta is 1 at y equal to 0, and at infinity we find that t is equal to t naught. So, theta is 0 at y equal to infinity for all time t more than 0. Now, this particular problem may be extended in a we have taken to be a infinitely bound solid, semi-infinite bound solid. Now, it need not be semi-infinite, it may be a finite solid. Now, in this case what we are saying, that here you can see the pictorial description, that here we have a finite width of the solid, and in this case we now place the origin at the midpoint in the y direction. Okay. So, this is the x direction, the y direction. So, because the midpoint we take it is plus b on this side and minus b on this side, that means the total length is taken to be 2b. Okay. So, plus b and minus b. The same situation, that initially the whole system is at T naught, and suddenly at T equal to 0 we give a temperature change to at this lower surface to T1. Okay. And again we make the same kind of assumptions, that isotropic, homogeneous, no heat generation, and with that we get from this particular equation, energy balance equation, we deduce that this is the equation. Till now the equations remain the same, and also after making these assumptions that there is no temperature gradient in the x and z directions. So, we get this particular equation. So, till now we have the same equation as before. Okay. Now comes the thing that now we start non-dimensionalizing. In the non-dimensionalization we go with the theta first. Theta is taken to be T1 minus T by T1 minus T naught, and the coordinate is taken to be this y by b. Now, here what we are doing, that we are not solving the or we are not writing the model equation for the entire domain 2B. We are assuming that the across the axis at the 0 there is a symmetry. So, we are going to solve only for 1/2 in the width direction. So, if the solve for 1/2, so we are putting in terms of B only, not in terms of 2B. And we are defining this non-dimensional time tau as alpha t by B square. Okay. Now, with this what we now find that the non-dimensional equation will come like this. And once we have found this non-dimensional form, you can see that at tau equal to 0, if you see that this theta is equal to t naught, okay. So, this will be t naught here. So, you find that theta equal to 1, and that tau this eta equal to +1, that is you put the value of B, okay. You find that there is a the temperature is still T1. You have given the temperature T1 at the two surfaces, at these two surfaces you have given T1 temperature. Okay. So, at B and plus B and minus B have given T1 temperature. So, you put the T1 temperature over here. So, you find theta reduces to 0, and at the midpoint this is shows the okay, this is not the midpoint, this is the other end, that is at minus B and plus B you find that theta equal to 0. So, either you can solve for the whole domain, or you can also, in this case if I want to take the 1/2 of the solid, that means we have, if my given system is like this, that here we have taken our origin. So, if I am going to solve for this 1/2 of this, then, and if I take them to be symmetrical, then if this is y equal to 0, so at y equal to 0, I can take, due to symmetry, I can take dty dy equal to 0. So, you can see that depending on the geometry we are considering, my boundary condition would change. Okay. For the problem on the both the sides I have T1 T1, it is becoming the Dirichlet condition. But if I consider only 1/2 of this, we find that on one side we shall be having the Neumann boundary condition, and this boundary condition is telling about the symmetry effect. Okay. So, it is a continuity, so symmetry effect. So, that is how it is coming. So, you can choose either this formulation or this formulation, does not matter whichever formulation you choose, you will obtain the same result. After this, we shall go for another situation as we have done for the momentum balance. Here we are having now the same situation as earlier for the energy transfer, heat transfer, but now we have the semi-infinite solid subject to a harmonic heat load. Okay. Now, harmonic heat load we are giving in this way, that the Qy, that is the heat load, equal to Q naught, some heat amplitude, into cos omega t, and again we are writing cos omega t in terms of the exponential form. We are writing it as real part of the exponential I omega t. Okay. And again the space varies from y equal to 0 on one end of the solid to y equal to infinity, that is a semi-infinite solid. Initial temperature is taken to be T naught. Okay. And at time t equal to 0, this kind of a heat flux is given to the particular surface at y equal to 0. Again we are assuming the material to be homogeneous and isotropic, and there is no heat generation within the solid. So, with these assumptions, we go back to the energy balance equation, and we deduce that this is the energy balance equation, this is the after these assumptions of dou by dou x, dou by dou z setting to 0, we get this equation. Up to this we find that we have the same formulation as before. Now, what we do that this particular thing we put in terms of the k, because this q is given in terms of the k, the our that initial that boundary condition is given in terms of the heat flux, and heat flux we are representing in terms of the k. So, we put in terms of the k. Okay. Now, we find that if we do this in terms of the K, we get this particular equation for this. Now, you see that we are on this side, we have put the Q in terms of the K, and because within the solid there the heat transfer will be due to the conductive heat transfer. Okay. So, that is how we are able to write in terms of the conductive heat flux. Okay. So, you will get the same expression as before on this. Okay. So, now we find that this is the kind of expression you are getting in terms of the Q and not in terms of the T. Why we put in terms of Q? Because our initial the boundary condition is given in terms of the Q. So, with this, if you do not do this, then we have to other way is that we have to convert this Q in terms of T. Okay, that is also possible, that you can put the Q in terms of T. So, whatever way you do, you will get the same solution. So, for convenience sake, we put in terms of the Q, and we find that the initial condition that it is Qy equal to Q naught at T equal to 0, and one end of the boundary condition is given like this particular sinusoidal heat load, and on the other side we have no heat load. So, we are putting that to be 0. Okay. So, that is how we are able to reduce the initial energy balance equation in terms of temperature to in terms of the heat. So, these are the references which you can refer to for more details about these problems. Thank you.